Hello, my name is Mark O'Byrne, and this is a presentation of my final year project. The title of my project is People Activity Tracer, and it was supervised by Dr. John McGrory. Just before I continue, I'd first like to thank John for his continued support and guidance throughout the course of this project. I will now give a brief overview detailing what this presentation involves. Chapter 1 will give an overall introduction to the project and will include these headings. Chapter 2 will detail the literature that was reviewed for the project and will include these headings. Chapter 3 will look at the design and implementation of each system or element within the project. Chapter 4 will go over the testing, results, and analysis carried out on each system and element. And finally, Chapter 5 will give an overall conclusion of the project. Project Introduction. The aim of this project was to design and implement a device that could detect the movement of people as they move through a particular environment. This animation shows the intended setup of the device. When a person walks past the device will produce a set of data. This data will then be sent to a database and will consist of the direction and speed in which the person has walked past the device, along with a date and time stamp of the event. Background. The prime areas in which electronic people counters are used include park walkways, shop entrances, and hallways. The data produced from these counters has various practical applications, including video surveillance, urban planning, resource management, and customer profiling. A possible add-on idea that was looked into was the incorporation of a Bluetooth detection system. This system would detect the presence of Bluetooth signals originating from devices being carried by people walking past the device. Goals and objectives. The main goals of the device were to be battery operated, use sensors to detect the speed and direction of pedestrians, date and timestamp each piece of data, and communicate the data to a database. The achievement of the objectives above depended on the completion of the following tasks: research into existing technologies, identify what components were needed and source the materials, design and implement the device, and test and analyze the effective use of the device. Ethical considerations. The main ethical considerations included ensuring that general data protection regulations were adhered to, and ensuring that the design of the device did not impede the normal flow of pedestrian traffic. Methodology. The methodology used for this project was the iterative approach shown in the diagram. History of people counters. Manual people counting was the main form of people counting prior to the year 2000. The first generation of electronic people counters became available in the early 2000s. These were mostly infrared beam counters. The second generation became available around 2005. These people counters used thermal imaging technology to count people. The most recent generation of electronic people counters became available around 2012. These people counters use advanced video imaging technology along with Wi-Fi signal detectors. Motion sensing technology. There are two main types of motion sensors. These are active motion sensors, which have a transmitter and receiver, and passive motion sensors, which only have receivers. Devices on the market. The first device you see here is an active motion sensor that uses infrared beam technology and has an accuracy of 80%. The second device you see here is a passive motion sensor, which uses video imaging technology and has an accuracy of 98%. Expectations of the device. The expectations of the device fall into three different areas. The questions related to ecosystem include: width of the hallway, 2.5 meters. Would the device be waterproof? Yes. Would a reflective surface be needed on the opposite side of the device? This was undetermined at this stage. Would the device detect cyclists and joggers? No. What would the height of sensors from the ground be? This was also undetermined, along with the distance between sensors. Technology. The method of detection was undetermined at this stage, along with what would the most suited type of sensor be. The most appropriate microcontroller was decided to be a Raspberry Pi. The method of powering the Pi was decided to use a power bank. The method of data transfer was also undetermined at this stage. The questions related to process include the sequence of data transfer. This would be a live transfer. The programming language that would be used would be Python. The logging of pedestrians was undetermined at this stage. The method of timestamping was to use a datetime library built into Python. The ability to determine direction. This was also undetermined at this stage, as well as the method of displaying the data. Comparison of sensors. 4 different sensors were researched and compared to one another. It was intended to test each one of these sensors to determine which sensor would be the most suited for use in the project. Remaining electronic components. The Raspberry Pi. A Raspberry Pi is a low-cost, single-board, credit card-sized computer that has similar capabilities of a regular computer. However, it can also be used as a low-voltage circuit controller. The MCP3008 analog-to-digital converter. This is an 8-channel, 10-bit analog-to-digital converter that employs SPI communication. Height position in research. This involved looking at research that studied the height of 18-year-olds in Ireland in 2014. The weighted height average was 172.3 centimeters. From this, it was determined that a suitable height to locate the sensors from the ground would be 86.15 centimeters. The first system that was designed was the detection system. The idea was to have the detection system consist of 2 sensors working together. 3 different sensors were tested for their accuracy at different distances and fastest time between detections. Comparing the results of each sensor, the sharp infrared distance sensor was found to be the most suitable. The sensor was then connected to the Raspberry Pi using the MCP3008 analog to digital converter as shown in the diagram. The next system to undergo the design process was the data processing system. The developments of this system are described in chronological order. The starting script was simply able to detect a change in output of each sensor. From here, the script was developed to increment a variable every time a certain distance, lower than a hard-coded reference distance, was measured. From here, a date and timestamp was created each time the variable was incremented. Each date and timestamp was then stored in a text file as shown in the image. The next development was incrementing the same variable when a distance measured was greater than or less than a reference distance. The final development of the script at this stage was incorporating a self-acclimating feature. This feature would allow the script to determine its own reference distance. This made the script more versatile, as it was able to work in hallways of different widths without requiring any code to be hard-coded. The next system to undergo the design process was the communication system. Private local area network. It was decided that a private local area network should be set up to facilitate the transfer of data from the Raspberry Pi to the database or other devices. MariaDB and PHPMyAdmin. After some research, it was decided that MariaDB would be used to create the database and PHPMyAdmin would be used for the administration of that database. MQ telemetry transport. MQTT was experimented with as a way of transferring data from the Raspberry Pi to other devices. MQTT is a broker and client communication system. Node-RED. Finally, it was decided that Node-RED would be experimented with as a way of displaying the data in the database. Implementation of each system. Detection system. Having determined the most suited sensor to be the sharp infrared distance sensor, it was decided that the final detection system would consist of a pair of these sensors. Unfortunately, due to the temporary closure of the TU Dublin Kevin Street campus, a second sharp infrared distance sensor could not be sourced. The second best option was to use one sharp infrared distance sensor and one HC-SR04 ultrasonic distance sensor. The diagram shows how each sensor was connected to the Raspberry Pi. Data processing system. Having implemented the final detection system, the data processing system could then be implemented. The first step involved combining the test scripts for each sensor and incorporating the self-acclimating feature. From there, the script was developed to calculate the time difference in seconds between each sensor detecting a change in distance. The sign of this result could determine the sequence in which each sensor detected a change. This represented the direction in which the pedestrian had walked past the device. The diagram shows how the direction of each pedestrian can be determined by looking at the sign of the calculated difference. This time difference between detections could then be used to calculate the speed of the pedestrian using the distance between sensors, which was 30 centimeters. This was the smallest distance between sensors that allowed for accurate detection. An additional feature was added to disregard false detections from an individual sensor if the other sensor hadn't made a detection within 1 second. Currently, the script cannot identify when a group of people have walked past the device or identify when 2 people have walked past the device walking in opposite directions. In order to get an idea of how often such events occur, a manual people count was undertaken for 30 minutes on 3 different days within the ground floor hallway of the TU Dublin Kevin Street campus. From this people count, it was found that the event of 2 or more people walking past a sensor in the same direction occurred 7.15% of the time, and the event of 2 people walking past a sensor in opposite directions occurred 1.66% of the time. Communication system. Private local area network. The plan was to run the Raspberry Pi in a headless operation. In order to do this, the IP address of the Raspberry Pi needs to be fixed. This was achieved by creating a static lease for the Raspberry Pi while configuring the local area network. MariaDB and PHPMyAdmin. MariaDB was used to create a database hosted on the Raspberry Pi. A table was created in this database that displayed ID, direction, speed, and datetime as shown in the image. MySQL connector was then used to write data to the table. MQ telemetry transport. This was implemented by installing Mosquito. Mosquito was then used to create a broker and client on the Raspberry Pi. Node-RED. This was implemented by installing Node Packet Manager, Node.js, and Node-RED itself. After some configuration, a flow was made that could query data from the database, which is shown in the image. From here, a pseudocode-style detailed GUI was designed but could not be implemented due to the lack of JavaScript knowledge. This GUI will be mentioned later in the future work at the end of the presentation. Device housing. The original plan was to use a watertight plastic container as the device housing. Unfortunately, due to the temporary closure of the TU Dublin Chemistry campus, one of these containers could not be sourced. As a result of this, it was decided to build a prototype of the housing out of cardboard. The housing requirements included being able to house the Raspberry Pi, breadboard, and power supply, as well as housing both sensors at a distance of 30 centimeters from another. The model of the housing was designed using Tinkercad and it was built using cardboard. The image here shows the positioning of the sensors within the cardboard housing, as well as the Raspberry Pi and breadboard. Testing results and analysis. Detection and data processing system. The test consisted of 50 instances of somebody walking past a sensor in a 2-meter wide hallway. The reason for testing in a 2-meter wide hallway was because the HC-SR04 ultrasonic distance sensor could not make accurate detections in a 2.5-meter wide hallway. From the test, it was found that the overall detection accuracy was 78% and that the system would have a higher detection rate of people walking in the left direction relative to the sensors. From analyzing this test, it was found that the non-detections were a result of the ultrasonic distance sensor making false detections. Communication system. Private local area network. This worked just as expected. Every time the Raspberry Pi connected to the network, it was given the same IP address. This allowed for the easy remote access of the Raspberry Pi using the real VNC viewer. MariaDB and PHPMyAdmin. This also worked just as expected. As the device detected people, the tab PC table in the people count database began to populate as shown in the image. As soon as a person was detected, the data was sent to the database and displayed in real time. MQ telemetry transport. This was tested by publishing a message to the broker on the Raspberry Pi and then subscribing to that broker using a client on a PC. This image shows the publishing of the text Hello World to the broker on the Raspberry Pi. This image shows the text Hello World being received within a client on the PC. Device housing. This was tested by running a basic sensor test script while the sensors were installed inside the housing. It was found that the gap between the ultrasonic distance sensor and the housing caused repeated false detections. This problem was somewhat overcome by placing a plastic sheet over the gap. Conclusion. Revised goals. The main goals of the project were achieved upon the completion of the following tasks. Number 1. Research into existing technologies. This was achieved by research carried out in the literature review. This research was of great help when it came to the design stage of the project. Number 2. Identifying what components were needed and sourcing the materials. This was achieved by identifying what was needed from each component and then researching and comparing components to one another. Number 3. Designing and implementing the device. This was achieved by firstly determining the best suited sensor for use in the device. From there, each system was then designed and implemented. Number 4. Testing and analyzing the effective use of the device. This was achieved by testing each system individually and ensuring that they would work accurately together. Future work. Future work that could further develop and improve the device includes using a pair of sharp infrared sensors as they are the most suitable sensors for the detection system, adding a second method of detecting people, perhaps by incorporating an accurate Bluetooth or Wi-Fi signal detector, including group detection along with the ability to detect when two people walk past the device in opposite directions, adding a feature that would alert people if they are within a certain distance of one another, perhaps through the use of an alarm and flashing lights, allowing the remote access of the database over the internet, implementing the graphical user interface design idea previously mentioned in the presentation, and making the enclosure out of a watertight plastic container. Overall conclusion. Overall, this project was a great success as each goal and objective was achieved. The device was battery operated, used sensors to detect the movement of people to an accuracy of 78%, stored the data obtained from the sensors with a date and timestamp, and also communicated that data to a database. This project has been a great learning experience and has helped me to better understand and appreciate electrical engineering. Thank you for viewing my presentation. I look forward to answering any questions you might have.